title of my speech is about the use of lung volume measurements to measure recruitment or derecruitment. What kind of lung volume are we talking about? We may talk about functional residual capacity, which is the amount of gas inside the lung at end expiration at zero pressure. Actually, in mechanically ventilated patients, we normally talk about end expiratory lung volume, which is the amount of gas inside the lung at end expiration at any pressure. So end expiratory lung volume should be qualified by the pressure at which it is measured. End expiratory lung volume at 10 of PEEP is something different than end expiratory lung volume at 15 of PEEP. So this is just to make it straight. We've been measuring end expiratory lung volume for many years in critical care, in intensive care. Personally, we've been using helium dilution technique by using a bag containing a helium mixture. And the concept is very simple. If we connect a bag with an helium containing mixture to the lung of the patient, then we make the patient breathe, either mechanically or spontaneously. At the end, we will have a change in the concentration of helium, which will be function of the amount of gas inside the lung. The mathematics are quite simple, but I will skip it for the sake of time. But it works. It is a very simple method. It is used very often in lung function testing, and we can adapt it to intensive care. However, it requires an helium analyzer, and it is a spot measurement. You can do it every so often. You cannot. It's not a monitoring technique. Now, we have automated methods that measure the lung volume by the so-called wash-in, wash-out technique. You can do it by measuring oxygen or by measuring nitrogen. This is an example of measuring the lung volume by changing the amount, by changing FiO2. You see here in yellow, FiO2, in blue, the expired oxygen fraction. You see, normally the expired oxygen fraction is lower than the inspired one. If we make a step change in the inspired oxygen concentration, for a certain amount of time, the lung will accumulate oxygen because the gas contained in the lung will have to increase its oxygen fraction. Then, when we do the washout, this amount of oxygen will come out of the lung. So we can measure how much oxygen stays in the lung, wash-in technique, or how much oxygen comes out from the lung when we decrease the oxygen concentration. And that is the washout technique. We've been studying different machines to do this. Initially, we've used this machine, which is an experimental machine. This one is the Angstrom Care Station. The principles are the same. The good part is that this is commercially available. It works. End expiratory lung volume is very useful in ARDS patients because ARDS patients, in specific, have a profoundly reduced lung volume. And I just showed you data, an example about changes in FRC from normal to ARDS. I will not repeat it, but many patients with ARDS have end expiratory lung volume lower than 1 liter. Now, what do we do once we have an available, safe, and accurate measurement of the end expiratory lung volume? Well, first of all, we should keep in mind that the ARDS lung is rather small than stiff. This is compliance of ARDS lungs plotted against the amount of residual healthy lung. That is the amount of lung that we see aerated in ARDS. And you see that there is a linear relationship between the amount of healthy lung and compliance. So compliance is basically a measure of the aerated lung in ARDS. So the first use we can do of end expiratory lung volume is to get a different approach to lung protective ventilation, to understand what's going on. And to understand this concept, you can probably use the simple concept of specific elastance, of specific compliance. What is specific compliance? Is the compliance of a unit volume of the ventilated lung. Is a compliance per liter of good lung. If I have a single lung unit and I apply pressure to it, it will change volume. It will change volume of 1 unit. If I now add another lung unit and I apply the same pressure, this second unit too will change of the same amount of volume of the first one. So you see, 2 units have double the compliance of a single unit if they are the same. The compliance of the system now is double, but the compliance of each unit is the same. That is, specific compliance is the same. This patient has 2 liters of residual lung, functional residual capacity, or end expiratory lung volume. If I apply 15 centimeters of pressure, the change in volume will be 1.2 liters. Now I have 1 liter of end expiratory lung volume. I apply the same 15 centimeters of water. Now the change is 600 milliliters. If the lung now is only 500 milliliters, by applying the same pressure, I'll have 1/4 change in volume. That is specific, when specific compliance is constant, and for a given change in pressure, the change in tidal volume is proportional to the volume of the lung. So now, if we want to have protective ventilation, perhaps we should keep in mind that the developed pressure will be a function of the available volume, provided the chest wall compliance is the same. And look here, I showed this slide already to you this afternoon. I have a little picture more. I just added this a few minutes ago. This is a PET CT scan showing areas of inflammation, and the areas of inflammation are there where the change in volume is bigger per unit volume unit volume of end expiratory volume. So let's put it in another way. If we have a patient with ARDS, he weighs 70 kilograms, his normal functional residual capacity is 2.5 liters. If I go to the book, his tidal volume should be 420 milliliters. We know that we should keep tidal volume at 6 milliliters per kilo. But if I apply the concept of tidal volume per unit FRC, when I go down with FRC, if instead of 2.5 liters, I have a very severe patient, 500 milliliters end expiratory lung volume, now per liter, per liter of FRC, I almost have 1 liter tidal volume. While in this one, which is a less severe patient, I have just 160 milliliters per liter of end expiratory lung volume. So the change in size of those alveoli is very different. This alveolus here increases 160 milliliters, while this one doubles its volume. Actually, triplicates its volume, because it starts from 500 and goes to 1.5 liters. But all these patients with different FRCs have the same 6 milliliters per kilo. These probably are not protected, while these are protected. But we have to get more data about this. Once again, going back to the fact that even with lung protective ventilation, we might have overstretching, because body weight, also predicted body weight, is not a very good indicator of the size of the lung in the first place, and moreover, of the size of the available lung. So ideal body weight is a very crude measurement. It's very good. It works 70% of the time. We should follow the rule, but keep in mind that we should check something else too. Now, we can use end expiratory lung volume also, 5 minutes, also to measure recruitment, to measure what happens when we change, as an example, PEEP, or when we apply a recruitment maneuver. If we have this region of the lung with a certain amount of open alveoli, and another 50% of the alveoli that are collapsed. So 50% of the lung here is derecruited, 50% is open. Now I put PEEP to 10. If compliance is 30, I should expect an increase in tidal volume of 300 in end expiratory lung volume of 300 milliliters. And the end expiratory lung volume will go up to 1.3 liters. You see, these open alveoli stay open. Actually, they get bigger. They get bigger exactly of the amount of the tidal, of the change that I expect from the applied PEEP. 30 milliliters per centimeter of water, PEEP is 10, so the change is 300 milliliters. At the opposite, if recruitment takes place, now I change pressure by 10 centimeters of water. What happens is that 2 rows of these alveoli pop open. Now the change in volume is not 300 milliliters anymore, but is 600 milliliters, because I'm not inflating 3 rows, I'm inflating 6 rows. It's not that I'm just inflating 1 lung on the left side, I'm inflating 2 lungs now with the same pressure. So the change in volume is double. So if I measure this end expiratory lung volume, I can tell you how much volume I have been recruiting. Simple. If the change is what I expect from compliance, then there is no recruitment. If it's more, then the difference is due to recruitment. And we have gone there to measure what happens in reality, and this is an example of control mechanical ventilation, low PEEP, versus control mechanical ventilation, high PEEP. 9 versus 15, actually it's 9.4 versus 16. Look at the change in end expiratory lung volume from 1.2 to almost 2 liters. Now, is only 7 centimeters change in PEEP, but the lung volume changes 700 milliliters. Now, if we go back to 0, FRC, end expiratory lung volume at 0, should always be the same. But here, it changes from 0.8 to 1. Why? Because we have recruited 200 milliliters of alveoli. And we have done a systematic approach to this problem, and we have been able to show that going from 5 to 10 to 15 of PEEP, the change in lung volume is more than what is expected by the change in compliance. Actually, we recruit some 200 to 250 milliliters of alveoli by increasing PEEP of 10 centimeters by 10 centimeters of water. So the concept is, if we measure end expiratory lung volume, we can get many informations. But what I want to tell you tonight is that if we measure lung volume, we can estimate, we can have another very effective estimate of the possibility of over-distending the lung. Because ideal body weight is very important, but the size of the lung I am ventilating is also more important, because it's a major determinant of the end inspiratory pressure. Second, if I measure actual lung volume, I can get a pretty good idea of how much lung I am recruiting. And this without doing a CT scan, because doing a CT scan is very precise, but it's not very simple to do at the bedside. Thank you very much.